Hi guys, welcome back to my series on explaining difficult A-level maths concepts so you actually understand them and are not just churning out formulas. So today we're going to be going over the essence of calculus, where it all begins, and it's first principles, because you are taught first principles in year 12, but little to your knowledge, it is so much, it's so important to understand it fully. And I want you guys to be able to make sure that you do understand exactly what's going on and can't just churn out this formula. So it's all well and good knowing that's the formula, even though it's not, because you're given it in the formula sheet. So what's important is you actually know what this means geometrically and how you can use it, because that's where you're going to get your marks. You're never going to see it in this form. It's going to be proving it with some function of x or even some trigonometric function, such as sine and cosine, that you will be expected to know how to do this from first principles. So yeah, first principles on first glance is complicated. There's a lot going on, especially someone who's new to A-level maths, which is when you learn this. You learn this very, very early on in your A-level maths journey. But you don't really use parts of it in the rest of A-level maths, and even further maths. Limits are quite not really looked upon. So anyways, this bit is confusing. Limits are incredibly intuitive, and once you've seen them, they will make sense. But you don't use them, and you're not really taught them in a way that makes sense. So anyways, I'm gonna quickly explain a limit to you. So a limit is basically as small as a quantity can get before it hits zero, and this will be important later. This is very, very, very important to our first principles. So a limit is essentially something between 0 and 0.00000 recurring 1. It is the smallest possible quantity you can get that is above 0, that's not 0, that you can use. They're incredibly useful. So when we're looking at the function, f of x, and I do like getting used to people using f of x, not always y. Y is brilliant, but especially when you switch to higher level maths, it's important that you get used to expressing things in terms of functions, because function notation is a lot more commonly used instead of y. So yeah, we're going to have f of x equals 1 over x. And f of x or y, that's another topic that I would like to cover in another video, because it is incredibly confusing to GCSE students. But yeah, so we have f of x equals 1 over x, and we're going to... I've drawn that quite well. That's less well. Actually, that's pretty good, I can't lie. I'm quite happy with that. So, yeah. The interesting bit about this curve is that when x tends to 0, the graph tends to infinity. However, you cannot, this is not allowed, this is how you break maths, is you cannot put x equals 0 and say 1 over 0 equals infinity. That's not allowed, because you cannot divide by 0. That is a fundamental law of maths. Dividing by 0 is impossible, full stop, not in this lifetime. We can't do that. However, what we can do is look at the graph, and this does get way more complicated. If you're interested, you can look up the, well, I wouldn't advise you to. You'll do it when you get to university if you have a passion for maths, but the epsilon delta proof of a limit is basically what I'm showing you what a limit is now, just very mathsy and very complicated. And it is that we can look at this graph and that we can say, okay, when we get closer and closer to 0, so when x gets closer and closer to 0, as it shrinks, the graph goes up and up and up towards infinity. So we can say, as x tends to 0, the graph, f of x, goes to infinity. So we can say that the limit, as x goes to 0, of 1 over x, as x gets smaller and smaller, we can say that that tends to infinity. That's okay. We can do that because all we're doing is it's pattern recognition. We're going close to 0 and the graph's going up, and we're going even close to 0 and the graph keeps going up, and we know that it is not going to intersect the x-axis and then go back down. That should be fairly intuitive. And this is very important, this whole idea of getting so infinitely close but not being at that same point is incredibly important in this. And I'm going to explain to you how. So now you know what a limit is, we're going to use it. And the classic example, I remember doing my first principles, that must sound very sad, but I remember differentiating my first function from first principles, and it is what everyone first differentiates from first principles. It is f of x equals x squared. The classic quadratic. You've seen that before. But, yeah, so this is what we're going to do. And it's important that we know, that this is the derivative function. Should probably have remembered that. But yeah. F of x equals x squared. So how are we going to find the derivative of this? 2x. But from first principles is how we're going to do it. And I'm going to prove it to you. So, what we're going to do is we're going to take any point, because when we are differentiating, we are finding a function that expresses the gradient, so y equals something x, or x squared, y equals a function of x, that tells us the gradient at a certain point. Because you can see, when we take that's not good. When we take tangents at certain points, the gradient's changing, right? Like, there you go, here it's negative, here it's 0, here it's positive, here it's steeper and more positive. You get the idea. And this whole idea of taking tangents is so incredibly important. That is essentially what this is. This is just taking an incredibly and infinitely precise tangent. So, what we're going to do to start is we're going to say that we're going to have our point x anywhere along the graph, and we are going to take our point x. So this is the x-axis, and then since it's a function of x, we're going along x, and we're going up f of x. So when we go up here, we are going to have a point which is x f of x. Yeah? Our x and y coordinates. It's classic. But anyways, so yeah. And what we are going to do is we are going to add a little bit. And this is all algebraically, so we can enlarge and shrink, and we can basically switcheroo with our whatever numbers we want. And we are going to have this second point, which is called x plus h. It's just x plus a little bit more, plus a number, plus any number we can make it. H could be anything. So x plus 1, x plus 0.01, x plus 0.00001, x plus a million. H can be any number. And that is incredibly important. It's just, is that when h is not 0, these are two different points. So we have our point x plus h here, which is x plus h, and then, very important that you have the x plus h inside the function, since it's a function of everything inside here. So then we have this, which is a function of x plus h inside of the function. And now, we're going to go back to GCSE Maths. How do you find the gradient of a straight line? You will remember that it is rise over run. Or more mathematically, change in y over change in x. Or delta y over delta x. Or, when we're getting into infinitesimally small quantities, dy over dx. That's our gradient. Remember? dy dx, that's our gradient function. dy dx equals to a certain function of x. And now this is all going to make sense, is when we do this here, how we find the gradient in this line is we go, okay, we do the change in height, or, yeah, what we've written here, delta y over delta x. Yeah, makes sense. We know this from GCSE. And that's what we're going to do here, is we're interested in the gradient of these 2 points. So that's just what we're going to do. We're going to do the change in y between these 2 points. So yeah, let's draw a straight line out between these 2 points. We're going to draw this out more. We're going to have x, and then we're going to have x plus h. And then f of x plus h. And what we're going to do is we're going to apply our straight line rules to this. So how are we going to find the gradient of these lines? Change in y over change in x. F of x plus h, our new height minus our original height minus f of x divided by our change in x plus h minus x. And luckily enough, these cancel, and we're left with this, f of x plus h minus f of x over h. Wait, right there, the exact same thing. The whole of calculus comes from straight lines. It is just algebra, but the whole concept of the gradient being this, change in height over change in run is the same. It's exactly the same. But now, yeah, it's not very precise, because let's say we have this, is that we've got our curve back. That doesn't show the changing gradient of the curve. So what we're going to do is we're going to bring back our idea of this limit. The idea of the limit being that the limit, when a limit goes to 0, it is still not 0. It is not 0, but it is so close to 0. So the gap between 0 and the limit tending to 0 is infinitely small. We're going to take that same idea and we're going to apply it to this. So what we're going to do is we're going to say, okay, as these 2 points get closer and closer together, so let's say, I'm going to draw it in red so it's easier to understand, is that when these 2 points are so close that they're basically on top of each other, the gradient is the line between the two is perfectly accurate. And this happens when h, the gap between the points, is infinitely small. H, the gap between x and x plus h tends to 0, so the gap is an infinitesimally small. It's that limit of h tending to 0 bigger than x. Because if h is 0, x to x and x plus h, if h is 0, then it's x and x. And you can't do a gradient between the same point. So the whole idea is that we have the 2 separate points that are separate, but they're as close as we can possibly get them, so that the gradient, so that tangent in which we draw, is infinitely accurate. And that is fine. We can do that, and you know that. Because when you take a tangent, you are not just going through one point, is that you're kind of going through two. But the 2 points are so close you don't notice, and it looks like you're just going through 1 point. That's a really important idea. If you can understand that, then you've learned so much, and you understand so much maths, and you pretty much have this concept under your belt. So that's the whole idea. So now to finish the video off, we are going to actually compute your first derivative. Now you know everything behind it, we are going to compute this, and we are going to find out what f prime of x is for f of x equals x squared. And yeah, what we're going to do is we are going to take our formula that we know, that we've just proved, and I've just shown you all the algebra behind it so you understand it, even though it is very complicated, so give yourselves a lot of time to process the information. Trust me, it's difficult. I've been there, and I remember it. It was not that long ago. So what we're going to do is we are going to draw it out, just because it's nice to have that little visual reminder. So we're going to put it into the formula. So we have f of x plus h, but remember our f of x plus h is x squared. So we are squaring everything in the bracket. Very important you remember that it is everything in the bracket. So f of x is 2, so f of 1 is 1 squared, f of 1 plus 1 equals 1 plus 1 squared. You have to make sure you square the entire thing. F of 1 plus x equals 1 plus x squared. We're squaring the whole thing. And this isn't just 1 plus x squared, it is x squared plus 2x plus 1. Remembering your binomial expansion, same thing applies here. So what we're going to do is we're going to plug it in. We have x plus h all squared minus f of x, which is just x squared, over h. Very important we keep writing this limit out, because it's a defining quantity. It's very important that we don't forget that. So yeah, we're going to now expand this, which we already kind of did earlier, but not in terms of h. So we're going to go x squared plus 2xh plus h squared minus x squared over h, not forgetting our limit. And we've got some very important steps here, is that we have x squared and minus x squared, so these are going to go. So then we have 2xh plus h squared. And what we're going to do now is we're going to notice we have a factor of h in each term. So what we're going to do is we're going to go 2x plus h over h, as h tends to 0. And we can actually cancel the top and bottom, leaving us with just 2x plus h. And then now we're going to evaluate this, which is basically we are going to let h get ridiculously small that it approaches 0, and we are going to take h as 0. So we're going to say h gets infinitely small and goes to 0, so we have 2x plus 0, which just leaves us with 2x, as our h's have gone. So in more formal writing you would write as h arrow to 0, which means tends, or you can write as h tends to 0. 2x plus h tends to 2x. So leaving us with 2x. So f prime of x, our derivative function, equals 2x. Boom. Done. That's it. That's your first derivative that you've computed. And this makes sense because let's draw out our original function and our derivative function. So we have x squared, and then we have 2x. This is f of x. This is f prime of x. And it kind of makes sense. When we take tangents, we know that the gradient is about there. It's like -2, and then here it's 0 when x equals 0. And when x equals about 1, the gradient is 2. And this makes sense because when x equals -1, it tells us that f prime of x equals -2. And do you see how this function tells us the gradient at a certain point? When x equals 0, the gradient is 0. When x equals 1, the gradient is 2. And when this gets steeper and steeper, the gradient gets steeper and steeper. And you will see that this just tells us the gradient at the certain points. And you can prove it with as many tangents as you want until you're satisfied. But f prime of x equals 2x. This shows us how the gradient changes of this function with respect to x. I hope that provided some useful insight, and I wish you guys the best of luck with your end of year exams or A-levels, and I hope you have a lovely rest of your day. Thank you.